Hi, welcome back. It's Colin here, and today we're going to be talking about factoring. Now, you may have already seen quite a bit of factoring in previous classes, and you might hear the word, oh, this is a factor of this, and I need to factor these things. That's interesting. Well, the word factor is actually a noun and a verb, right? A factor noun means, well, it is an item, like a number, where if you multiply that number by something and get an answer, like A times B equals C, then A and B are factors of C, right? Now, if I wanted to factor C, the verb factor, I want to take C and find out how do I split it into A times B, right? Sometimes taking a number like 32, we want to factor it. What can I take two things that multiply to get to 32? Well, 32 is even, so I know that 2 divides it. So why don't I say it's 2 times 16? That's great. I have officially factored 32 and into two factors. One factor is 2, and the other factor is 16. Now, if I wanted to do a prime factorization of 32, we would continue this, right? We would break 16 down into 2 times 8, and then we'd break 8 down into 2 times 4, and then we'd break 4 down into 2 times 2, and look, 2 times 2 times 2 times 2 times 2. Oh, look at that. 32 is actually 2 to the 5th power. Well, the same way that we factor integers, there's actually a very analogous way to factor trinomials, binomials, polynomials in general. Now, many of the polynomials that we'll be working with are going to be binomials and trinomials. A binomial and a trinomial, you may have guessed from the Latin roots of the prefixes, are two-term polynomials and three-term polynomials, right? Bi meaning 2, 3, tri. Why don't we try this? I have a polynomial here. It's a trinomial. It has three terms, x squared, 2x, and 1. Now, my goal is to factor this trinomial. I imagine factoring it into, well, a couple of factors at least, right? The first thing I like to do is check the coefficient of my leading term. Now, the leading term is the term with the highest degree. I can look at the coefficient of the term with the highest degree, and here that coefficient is 1, right? When we have no space next to a variable x, we assume that there is 1 times x squared there, right? There is one of them. I like to have a 1 in the leading term if I can, right? Here we have that, so we can move on. I think one of the best ways to start off doing this is go to write an equal sign there and say, I want to factor this into two binomials. And let's just see if we can do it, right? Well, I see through multiplication of these two things, we have to get an x squared, right? Now, x squared is actually just x times x. Okay. What two numbers multiply to 1 and add to 2? Well, two numbers that multiply to 1. Well, the easiest one I can think of is 1 times 1, right? 1 times 1 multiplies to 1. Now, do those two numbers add to 2? Well, yes, 1 plus 1 is 2. So 1 times 1 is 1, and 1 plus 1 is 2. I think I could utilize this here. X plus 1 times x plus 1. Now, I see why I put the 1s in here, right? But why did I say plus? Well, as it turns out, this question that I was asking actually had a little bit more to it. It's a bit more nuanced. Is what two numbers multiply to positive 1 and add to positive 2, right? Well, I chose these numbers because they multiply to positive 1 and they add up to positive 2. I'm just looking at the coefficients of each one of these terms now, right? All right. I've officially factored x squared plus 2x plus 1. Now, I guess you could say, well, that's just the easy one, Colin. Why didn't you do one of the hard ones? Well, I just wanted to get going first, you know? I wanted to see exactly what's going on with this process. And is there a way that I could, like, check my answer, you know? And it turns out the answer is yes. You can check your answer. There's almost always a way to check your answer, actually. Now, if you're going to factor something, it's almost kind of like dividing it into two pieces, right? I can find two pieces that multiply to this bigger object. Now, how do we undo division? Well, multiplication, right? 50 divided by 2 is 25. 25 times 2 is 50. Oh. Okay, so if I took this and kind of divided it into two pieces, I should be able to multiply these two pieces, and they would equal this, correct? If I'm saying that this expression is equal to this expression, then if I perform these operations in the correct order, remember using our GEMS technique, then I will be able to get this precise expression here. Okay. Well, we like to use the, I guess some people like to use the FOIL method, right? The first, outside, inside, last. You could also think of this as a distribution over addition. So we're going to multiply x plus 1 times x, and then multiply x plus 1 times 1, and then add those. So however you'd like to do it, maybe we'll do it both ways. Let's call this the FOIL. First, outside, inside, last. That means let's multiply the first ones first. X times x is x squared. We multiply the outsides, meaning the first and the last. X times 1 is x. Now, inside, multiply the insides here. These are the outsides. This is the inside. X times 1. And now last for L, the last of them. 1 times 1 is 1. Now if we collect like terms, we're going to have x squared plus x is, there are 2x and plus 1. And look at that. We're using the FOIL method. We've multiplied these two factors, and they equaled the original expression, the original polynomial that we had. And that's exactly what we wanted, right? Now, I just wanted to show you a little something. If I wanted to maybe multiply without using FOIL, I could do what I talked about a minute ago, which is distribute x plus 1 to each term of this sum here. So if we say, let me get a different color, equals x plus 1, taking this and distributing it to the x, and then distributing it over to the 1. So x plus 1 times x plus x plus 1 times 1. Okay. Now this is going to give me x plus 1 times x. I can use distributive property again, the x distributing inside this sum here. So we have x times x, which is x squared, plus x times 1 is x, plus x plus 1 times 1 is just x plus 1. And now we've left ourselves here right at the same spot. X squared plus 2x plus 1 after collecting like terms. Okay, let's test our skills a little bit. We have this first one here, x squared plus 3x minus 4. And the goal here is to factor this trinomial. Now, typically what I like to do is just go ahead and write out a couple of parentheses there. Because this is really what I want to do, is split this trinomial into at least two things, that when you multiply them, you get this. Right? Now, the first term, the leading term here, is x squared. That means I know both of these got to start with x. Right? I looked at the coefficient of the leading term, and it was 1. So I'm going to just say, why don't I just try throwing an x in the front? Now, for the empty space here, to fill in the blanks, what I want to do is find two numbers that multiply to -4 and they add to +3. They multiply to -4, but when you take their sum, you get +3. Well, we got to just think of a few things. There's only so many options that of numbers that multiply to -4, right? So let's just split -4 into factors. Well, there's -2 times +2, right? But when we take -2 and +2, we take their sum, we get 0. But 0 is not equal to 3. So that's not going to work. Now we kind of got this thing going. We multiply to -4. Well, +4 and -1 gets you -4 when you multiply them, right? +4 times -1 gets you -4. Okay, so we have that they multiply to -4. Now when we take their sum, +4 minus 1, oh, that's +3. Hey, we did it. Okay. Well, what did we do? Well, we found two numbers that multiply to -4, and their sum is +3. And how does that help us? Well, check it out. We'll say +4 minus 1. And now we're done. Do you want to check your answer? Try a FOIL method. Maybe pause the video, or you could distribute this over and check to you get this same expression right here. Now let's check out this next one. X squared minus 7x plus 12. Now you know how I like to go ahead and throw up my parentheses first. And we say, look at the leading term here. It's just x squared. We pretty safe bet that this first term in both of these binomials is going to be x. Now, let's find out the rest. What two numbers multiply to 12 but add to -7? Multiply to +12. I need something that multiplies to +12 but adds to -7. Well, let's think about the factors of 12, right? We have 1 times 12, 2 times 6, 3 times 4. Well, that's it. So we have 1, 2, 3, 4, 6, and 12. Which of those numbers that multiply to 12 add to -7? well, you know what? Since this is positive, I can almost bet, and this is negative, then I know that the factors of 12 are going to be two negative numbers, right? So let's see. 4 times 3 is 12, but when you add 4 times 3, you get positive 7. But negative 4 times negative 3, that equals positive 12. But when you add negative 4 and negative 3, you get negative 7. And that's precisely what we wanted. So why don't we fill in the blanks here? All right. So now go ahead and pause the video and see if you can make sure that this answer is correct, that we've factored number 2 correctly. All right, let's move on to number 3. Notice that now we're working with a trinomial that has a coefficient in the leading term other than just 1. Look at this leading term here. Now, I'm still going to write up my parentheses here. And I'm going to say, well, these leading terms always wind up multiplying to this leading term, right? The leading term of this binomial and the leading term of this binomial will always wind up multiplying to this one. So really, I just need to say, well, what two things do I need to multiply in order to get to 2x squared? I would say, let's just try 2x times x. All right. Now, if I was going with what we did before, I would say what multiplies to 12 but adds to 10. Yikes. This doesn't work here. Check it out. This 2x is going to multiply to both the x and whatever I decide to put right here, right? So now there's kind of a lot of moving parts, and I'm not necessarily sure how to do it. Uh-oh. Aha! I just thought of something. On this third one, what's something that you notice of all 3 of these terms? The coefficients of each one of those terms has a factor of 2. What I mean is that they're all even. Well, if they all have a factor of 2, then it looks like we could actually factor out a 2 from each term. Now what does that mean? It means that I could rewrite this expression as 2 times something. 2 times x squared, 2 times 5x equals 10x, and 2 times 6 equals 12. Now we have 2 times a polynomial, and it looks like we could factor this polynomial on its own and say 2 times that factorization is going to be this polynomial. You see that? So why don't we try it now? 2 times throw my x's in. Now I need 2 integers that multiply to 5. There's only so many numbers that multiply to 6, right? There is 1 and 6, and there's 2 and 3. Which one of those adds to positive 5? Well, 2 and 3. Now, if you go ahead and multiply all 3 of these factors, you will surely get this trinomial as your answer.
Now, there's a very special topic that comes up when we're talking about factoring. It's the difference of squares. Now, you might be thinking to yourself, what are you talking about? Square minus bigger square equals happy face? No, not exactly. But the difference of squares is actually talking about square roots, right? And square numbers. Squares are numbers that have square roots, right? That are integers. So, for example, 25 is a perfect square, right? Because 5 times 5 is 25. Maybe we can think of, I don't know, 121. That's a perfect square because 11 times 11 is 121. Now, what does that have to do with factoring difference of squares? Well, what if we had something like a variable squared and a number squared, right? What I'm talking about is the expression x squared minus 36. Can we factor that? You betcha. Check it out. I know that x squared is a perfect square, right? X times x is x squared. Now, 36 is also a perfect square. If you see the difference of two perfect squares, we know that we could factor it just like that. X plus 6, x minus 6. And that pattern stays true for any of these. So check this out. Maybe we want y to the fourth minus 121. Well, I could say, well, that equals, what's the square root of y to the fourth? Oh, well, y squared times y squared is y to the fourth, right? Because if we have the same base, we add the exponents. So I could break this into my two pieces here, y squared plus 11, y squared minus 11. If you don't believe me, pause the video and go ahead and use your FOIL method or your distributive property over addition and check that these actually are equal. I think you'll be pleasantly surprised.
There are a few interesting situations that could come up where you'll be able to utilize the difference of squares method of factoring. That's really going to help you out now and in the future when you get to pre-calc and when you get to Calc 1 and Calc 2. Now, the reason why it keeps coming up is because factorization usually winds up leading to simplification, right? And when we simplify a problem, we're breaking it down into smaller pieces, more manageable pieces that we can all kind of tie together at the end, right? Now, something like an expression y cubed minus 121y. What does that have to do with the difference of squares, right? Well, I'm not sure yet, but if I wanted to factor this expression, the first thing that I notice is that both of these terms have a single factor of y in it. So that means I could kind of use the distributive property of multiplication over addition to my advantage. I kind of undo distribution, right? I can pull out a y from this expression and say, well, y times y squared is y cubed minus y times 121 is 121y. These two are indeed equal to each other. Well, now we kind of had a difference of two squares hiding in this expression, didn't we? Right? So we were one step away from being able to say, ooh, I recognize a difference of two squares there. I know how to factor that. That's easy. Because we all know that 121 square root is 11, right? So y plus 11 times y minus 11, and we're done. Now, you didn't really think that the difference of two squares was going to come up any other time than just seeing that, right? As it turns out, it could be kind of hiding in somewhere, maybe even something like this, where the coefficient of the leading term is not 1, right? That each one of these terms has a factor of 3. Now, it might not be entirely clear that 108 is divisible by 3. There is actually a neat division trick, right? A division test for 3. If you take any number and add its digits, the resulting sum, if that number is divisible by 3, then the initial number you were counting the digits for is also divisible by 3. Go ahead and try it. It'll work for any integer. Here I see 8 plus 0 plus 1 is 9. 9 is divisible by 3. So that means that 108 is divisible by 3. Check this out. 3 times x squared minus 3 times what is 108? Well, I need to divide. 3 goes into 10 3 times with 1 left over. And we're left with 18. 3 goes into 18 6 times. Now, this expression equals 3 times x squared minus 36. Whoa! That's screaming out to me. Difference of 2 squares. I know how to factor that. And we're good to go. Now, you may be asking yourself, why is factoring even really all that useful? Like, why do I need to know how to factor these trinomials and binomials and difference of squares and yada, yada? Well, I'll tell you. You're probably not going to like the answer, but it's because you're going to use it a whole lot, right? You're going to use it in this class. You're going to use it in pre-calc. When you get to calculus and calc 2, factoring really helps. And the thing is, the reason why is that factorization usually leads to some kind of simplification of the problem. And that's my favorite thing to do with any math problem is simplify it into smaller, more manageable pieces that I can tie in together at the end.